this is a long time test case model that, developed back on the Housatonic days. That was a few years ago. It's patterned after Yin and Lee sediment transport case, where they had non-cohesive sediments looking at scour and deposition patterns along a bend. And we've just used that because it encompasses several nice features. Number one is pretty tight little model domain. We know some shear stresses that were used from the flume study. They have a series of predefined flows that they used in the study. So we kind of know what grain size should be being moved under certain conditions. So it makes for a nice test case. It has curvature, which is nice because now you're this issue of the bed load. The problem with bed load was found with this test case because the cells on the interior of the bend are smaller than the cells on the exterior of the bend. And when we were simulating a straight flume that had all the same cells, that I got perfect mass balance, then I threw the curve example at it and realized, nope, not quite so fast. So anyway, so it runs fast, pretty contained, and it's just a 3-hour simulation period. It literally runs on my machine in about 3 or 4 minutes for a run. We have it set up with 3 size classes. However, I'm only using class 2 right now. So classes 1 and 3 actually have no sediment configured. There's no, the water coming in has 0 concentration of TSS, so the only sediment in the system is the sediment in the bed initially. And this particular test case has morphologic feedback turned on, and but that's the nice. We can play around with it really quick, and we'll be able to see what's the impact when we add and subtract some of these, or turn on and off some of these options that are in the sediment transport model. So main form, we've got it here. It'll be on the the name of the project is called SEDZLJ No Tox. We're going to use the same model tomorrow for the hands-on for toxics transport, hands-on work. So it'll be tomorrow. It'll say SEDZLJ Tox. 180-degree flume. So that's the model we're going to load up when we get to it. As I said, there's 3 size classes here. We've got sediments turned on. That's the only parameter that's currently activated in this particular model. Step into the configuration of the sediment model itself. We've got 10 bed layers, but I'm only parameterizing the bottom 4. So sediment time step, 1 time second. 1 second time step. And the time step in the hydrodynamic model is 0.05 seconds. So this is essentially equivalent to a 20 skip count of 20. This particular model doesn't use dynamic time stepping, not needed in this little flume example. Doesn't really buy you much. But anyway, so we have that as the our sediment time step. We have bed morphology turned on. We don't have, there's a bed slope change, and I haven't tested that very thoroughly. I don't have that turned on right now. I didn't mention this before, but you do have this delay, or you have a time to start. And that's helpful for kind of dealing with initial condition ramp up issues if you're using a cold start model, and especially if your bed is highly erodible. But you get the shock to the system and the hydrodynamics when you turn on the model and things start eroding and doing crazy stuff because it's just the shock of the initial condition expecting the results. So this gives you the ability, and we've added this to the original sediment transport model also. So now it's for both. So you can basically start up a run, let it run for a couple of days, let things kind of stabilize in the hydrodynamics, and then turn on sediment transport. This is the HMIN that I was referring to. The default was, or the hard-coded value was 0.5 meters. I've set this quite small to only 5 millimeters here because this flume is only 5 centimeters thick to the water column, so it's real small. These others down here, these are the defaults, don't usually change, and this is usually mostly for testing and doing some more, I don't even, necessarily probably don't even need to be on the main form, but they are part of the main controls. And it's important to know, but you can specify a constant shear stress for the model, or you can just fix your D50 to a certain size class if you don't want it to automatically compute, things like that. Just run through these. You guys have seen all this stuff now. I've turned on. This is a really important for this model to make sure that we're removing the bed load and putting it out of the upstream cell and into the downstream cell while still maintaining mass balance. The erosion rates used. Now this particular test case, let's go back here. This is just kind of this is not based on actual data from the Yin and Lee work. I was just playing around, getting the model to behave with a certain size class. So I have picked this 250 micron size here as my test subject, you might say. So it's, simplified 100% of the mass, but if you, right here, you can't see any thickness. You got to go down to the bottom to see the 4 active layers that have sediment in it. And so the initial condition, notice my bottom elevations here. I have right now fixed to a ramp of 0.2 meters to 0.3, just a small little bit of a slope on the sediment surface. However, that cell right there is actually 1,000 meters deep. It's just a big bucket. I put at the end of the computational bucket so that any water that flows through the flume and out of these bottom cells is captured within the model domain, so we can calculate mass balance. And we'll do that this afternoon. I'll show you guys the tools that we can do to do that. So this is a nice little closed system testing. I think it's very useful little application. So here's the boundary conditions. This is the just a hydrograph that just basically goes up for 1 hour and down for 2 hours. Is the actual hydrograph test case. Water's coming in, the upstream end uniformly distributed, and downstream we have hydraulic control structures. So we're taking the water that comes into that cell and just passing it down to, they're all going into the same cell downstream. So we fully have a closed system. SEDZLJ zone, one core applied uniformly. What the top layer is 0.2 meters thick. There's 4 sediment layers, 5 centimeters thick each layer. And they're all size class 2. And roughly, well, not roughly, well, 329 kilograms per square meter in the sediment mass for class 2. So what does this look like? Oh, yeah, that was just a skill plot. So longitudinal profile, this is at a fixed J along the axis of the flow. So there's your slope, your water level. Top, sediment bed, the whole thing sloping down. see that's kind of the model configuration. Here is animation showing here at the bottom we have total suspended solids in the water column above this line. Below the line we're displaying the sediment mass in kilograms per meter squared. Because thickness affects that value, you'll see the formation of the active and deposited layers, and as they shrink and grow based on applied shear stress for the model. So we'll just turn this on now and watch it as we run through the hydrograph. You see we're depleting the active layer, but then it's replenishing again. That actual thickness has to stay constant based on the shear stress in the D50. So when it gets finished, you can see this is with morphology turned on. Notice that your bed surface is no longer, it's not stationary. The bed, as it erodes, the bed is actually changing its elevation, and the sediment columns are staying, the bottom is like a hard bottom. You could think of it like down here, it's bedrock. But up here, this is just an erodible surface. When you turn morphology off, it's kind of the other way around. So here we have deposition, or actually very little scour in this case, happening through the middle portion. This section here is the bend of the flume. And in plan view, same time period, we can watch scour and deposition. So this is actually the sediment layer thickness here. So we're getting some scour through here, starting to get some scour and some deposition on the leading edge of the curve. As it comes out of the curve, we're getting scour along the outer edge and deposition right there. Exits the curve. Now, the data, and this is not calibrated, or we haven't tried to make it work, but the data actually shows the point bar formation right here. And we're getting it further past the curve. That's, I mean, we have a single size class. It's not representative of real world necessarily, but with this tool here, we should be able to, take the effort to actually put in the correct size distribution. Well, the test cases I was saying was actually 100% non-cohesive. It had a D50 of 1 millimeter, so it was kind of a coarse sand, but with a distribution. I forgot what the fee was, but basically, it followed a uniform distribution with a D50 of 1 millimeter. So get around to probably doing that someday and seeing how the model behaves. That is really it. So let's jump out now. Let's get everybody to load up the flume test case. Now we should have, I think the output and everything's already there. So let's just go ahead and slice and dice it a little bit so you can kind of see how this process works. This is our 2D slice view up here. And you went through loading just initial conditions and any of this stuff yesterday, or? Okay. Yeah. By default, if you just click on the button, it'll allow you to view the initial conditions, but by default, it'll go out and try to load the model results if there are any. If they're not, it just assumes that you're just going to look at initial conditions. That can get you in a little bit of trouble sometimes. If, for instance, you've got a model, it's running, and you start editing it because you're getting ready to create a new run. So let's say you added a constituent, like dye or something, or you changed your number of size classes, and you inadvertently click one of these buttons directly and not view initial conditions, EE now is confused because what you've got loaded is one set of parameters and different things than what's actually the model was run with at the time. So it won't crash the model, but it'll tell you that there's a mismatch, that things don't, aren't connected up right. So good process is probably load your model, create a new project, and save it out before you start making changes. But you don't have to do that. And oftentimes I forget to follow my own advice, and I start making changes and then realize, whoops, But nothing will crash. You can just, back out of the viewer and go save your model, and then you're back in business. So anyways, so let's just view model results. Again, like I said, there's two different ways to extract model information. In this particular very simple model, slicing either an I or a J makes sense. The J is what we want to slice, because the model is configured. When you look at a cell map, it'll be horizontally configured. So it's got 37 rows and 9 layers in the J versus the I. So just slice it, 7 or 8, somewhere in the middle of the model. Say OK. Now, you get this, and you have control. Shrink this down so we can see it. There we go. Left to right. Not much room on this screen. There we go. To change what you're displaying here, easiest, what I almost always do is I just right mouse click on the legend. And that brings up what you want to display, this menu item here. And then you have, under general options, you can add or remove timing frames. If you've got more information, you can add IDs to your, basically it's an I or J value across the tops. Sometimes useful, but most of the time not. Switch your display of time from calendar to Julian time. The precision, that's the number of decimal places shown up. And this by always, right now it's just kind of the way it works. EE always displays everything in days. So if you want it in seconds, you can just change this and then just change your calendar format to hours and minutes and seconds, something like that. Then you can see it in, down to the second value. But anyways, that's how you change your timing here. Water column. This is what's going to display. If you turn that off, you're not going to see the water column at all. So turn that on. Then you can optionally show the grid or not show the grid. Then you can pick your parameter that you want to display, and notice the things that are grayed out, they're not simulated. So you can only display what you've simulated. Vertical exaggeration. Any kind of vertical plot, especially through a really big model domain, if you don't apply some vertical exaggeration, you won't be able to see anything. It'll just be this little line across the plot. So we have control over the vertical exaggeration. That applies actually more so to the velocity scale here, actually, than thinking more of the 3D. You control the vertical scale just simply by changing your scale of your y-axis. So anyways, we want to do sediments. Then you can set, your concentration, and these are fixed. These are not automatic. When you're doing the 2D plan view, you have an auto scale option that will go out, look at all your data, and then display your color ramp based on your minimum, maximum associated with what's currently displayed. Very useful. Probably should be here, but it's not here. So right now, for the longitudinal profile plots, you have to specify a range that's representative. So you kind of have to know how the model is going to behave a little bit. I mean, you can always just bounce back and forth. It's all very dynamic and interactive, but we know that it should be around 1500 for the upper range for the concentration in the water column. And then you can specify, do I want to look at class 1, class 2, class 3, whatever, or I just want to look at total solids, which is what I want to do here. Although you would get exactly the same result if I did this, because I'm only simulating one class. So we'll just click it back over to total. We're not simulating ice, so we can't see the ice cover formation and melt on top of this example. Sediment bed. This has been a little flaky recently, but we're going to turn on sediment bed. Now, I'm not going to change anything. I'm just going to say, okay. Oh, the other thing that's important to note is maximum layers. So this is, let's say I have a model, it's got 20 layers in it, but I don't really care what's happening at depth. It's really, I just only interested with kind of what's happening in the top 4 or 5 layers for visualization purposes. This is just for visualization. You can specify the maximum number of layers to display in your visualization. So if I'm simulating 10 layers overall, I might want to put 10 in this particular case. That should, cover my what I'm, seeing in this model, because in this, I pretty much want to see everything. There's a lot of settings here, and if every time you have to go into this, you have to do all this stuff, it's kind of tedious. So EE has the ability, let's just say okay to this, and then I can display it. Did I tell it? Sediment mass, total sediments. Here we go. But now I have to also set axes if I want to have a lot more control. This is the default, and it works, largely fine. But there is 2 files to get consistent plots out that you need to load. If you hit F2, it brings up a list of your potential help things that EE can do generally with this profile. Now, not all of these things are totally applicable. I don't think this is okay. That is. Actually, most of these are okay. Sometimes it'll say things like integrate the curve, but you're not looking at a curve. So can't integrate the curve. But here, what we want to look at is these options here. You have the ability to, whatever your settings are that are displayed, by the time you get your scales right and your axes right and all that information and your color ramps the way you want it. And that's great for this run, but I got a run to do, another run, A, B, C, D, and I want to generate a report, and I want to generate a series of plots, and I want them to all look consistent. So you can save a layout to a file, and then you can just load it right up and see exactly everything's all laid out just the way it was, including timing frames, where your legends are. It's all saved in the layout file. So I've already got one on your distribution disk, so you should have one. So I'm going to, if I can get out of this crazy compressed screen here. Here we go. I'm going to load it up. It should be, yeah. So that's these 2 files. This one's, we'll be playing with this one tomorrow. This is the configuration for the toxic test case. But this is the one we want to play with. It's DS, Dynamic Solutions Graphics File, DSG. It's just that's what this DSG file contains, is all the configuration settings to get these plots looking the way you want them. So you just click it, and there, and you get all your settings the way you want it. Now, there is another control that probably should all be in the same file, but it's not right now. So just put that on the list of things that need to get done. Is the size, how tall your plot is, how wide your plot is, because when you're generating plots for a report, you want them all to be consistent. The same size, same scale, so that they look, identical as you look. The only thing changing is the information on the plot, not the plots themselves. So to do that, go back to F2 here. I loaded the format using, this is save format and load format buttons up here, but I can control my plot size using the Alt-K and Alt-L. Alt-K will save it and Alt-L will load it, and what that does is that'll force my plots to all be consistent in size. So Alt-L to get your consistency for size and consistency for what you're plotting, and all the parameters on the plot is those two buttons. Like I said, they probably should just be one, but that's the way it started off and just hadn't raised to a high enough priority to fix it yet. But I mean, I'm assuming you guys have seen all this stuff, but you can use a Control G and go straight to a specific date. It can be Julian or calendar. Page up, page down. Shift page up, page down operates in a times 10 multiplier, and Control page up, page down 100. So you can just hit Control and scroll quickly up and down based on where you are in the model and how far you want to go. Home and end jump you to the first and last of the time snapshots. Now, when you're in this view here, I'll just close this out now. I would be at a disadvantage if I tried to load the size of my image right now. It'd probably be way too long, because this projector has a really small resolution or poor resolution, so I have to squeeze everything to get it on here. So I'm not going to use that, but that's how you do it. Now, you can also, you noticed that, well, let me just go back to it. When you're in a profile view here, like this, you can use the plus and minus key to scroll through your I or J. So you can just slice through the model a different I or J with just using the plus and minus key. So in this case, we're looking at a J of 8. So if I just press the plus key, now I'm at 9, and then 10, well, there's no active cells at 10, because that gets over the top of the model. So it says, sorry, nothing found. So I'll go back down, 9, 8, 7, 6, 5, 4, etc. And so you can just slice and dice your model that way. And then once you kind of get it set up the way you want it, there's, again, a range of different ways to go to a particular plot or a particular time. You can use a scroll bar up here. You can use Control G, and jump directly to a specific date or time. Or one of my favorites that I use a lot in real modeling is using the timing frame here to jump to a particular time. We'll do this afternoon with the Chuck Coop, but it's a quick way to jump to like the hydrograph peak or the hydrograph recession limb. So you see your hydrograph, and you just right mouse click and say, go to that time, and it takes me straight to that time. Now in this case, it's somewhat trivial. So like here, if that was my peak, this is only a 1 hour period. And again, it's all user defined. So I told it 1 hour, and I'll show you how to do that. But if I want to go right to the peak, I just go to the peak with my mouse, right mouse click, go to time, and now that's the peak time. So These are just ways to get around temporally in your model. Yeah, so we'll just turn on the animation. And I do not want to animate to an AVI, but it's easy to do that. I will tell you this, it's interesting. Since we all kind of ported it over to Windows 10, we use an AVI format and a codec in EE right now that Windows 10 has two video players. It has the old default Windows media player, and then it has a video player. The video player won't play these files, but the media player works fine with it. And then all these third-party like FLC and all the other video utilities that are out there, they all play it fine too. But if you're on Windows 10 and you just kind of double-click on it, it'll say, "Yeah, sorry, can't do it," unless you've configured the AVIs to work with the media player. No, I don't want to do it. So we just now, when you're generating an animation to the screen, it just starts from whatever your current time is. There's no control over like how long it'll play. It'll sit there and just run continuously, starting at your current time and just run until I press a key to stop it. Which is nice. And sometimes it might be nice if we limited, stop it after a certain amount of time. But anyways, this is kind of the way it works right now. But here this is the inner, the outer edge of the bend. So notice when we were looking at a J8, which is closer to the outer bend, we were seeing less scour through the middle, through the bend. But here, you're seeing, more scour being picked up around the outer edge as it goes around the bend. And so morphology's turned on. You're getting all your hydrodynamic feedback between the model and the domain. And this animation is using the updated probability of deposition for the non-cohesive. I mean, we can play around with this some more if you want, or why don't we I'd like to play around with some of the options and see what impact it has on the results. I think the first one that I want to do is just turn morphology off so we can compare the two. So let's do that. First off, I'm going to create a folder that I'm going to work in for making my changes. Because I'm going to leave what I've already got done, even though it only takes a few minutes to run. It's still a few minutes that I don't have to wait next time I try to do it. So I'm going to save this out. And I do this a lot. I don't know, this might be helpful to you guys, but especially when I'm generating a whole series of runs and I'm just changing something, a lot of times I'll change the run title up here just a little quicker and easier, especially let's say I've got calibration run 22. And so when I get ready to save out calibration run 23, I don't want to have to type out calibration run 22. I'm really lazy about typing. So if all you have to do is if you right mouse click on the open folder here, it will copy that text into the clipboard, and then I can just paste it and create it and then modify it as I want. So here I'm going to just right mouse click on that, jump up a level, create new, paste that run description in there, and then just add delete me 00. And then the next time, all I have to do is change from 0 to 1 and 1 to 2. So it just keeps me from having to type. I know I'm just lazy that way. I'm sorry. So with that, now I have a new folder, and I'll save it out. Go to sediments, and the only thing I'm going to do is turn off morphology. and then we'll save it out and run it. And then run, and I'm assuming everybody's pointed to the correct run, and as I said, in my case, I'm running 8.4, but you guys will all be running 8.3. And this only runs for 3 hours, so 0.125 days. It should just be done in a few minutes on everybody's machine. He described all the meeting Dinesh yesterday and the day before, all the fields. Yeah. I mean, one of the things I find really helpful on real models is the flow summaries that come up at like every 10 blocks. So you got these blocks, about every 10 of these. You get the summary that tells you how much in total. It does a little mass balance around the model, gives you all your flows going in and out through open boundaries, through flow boundaries, and just kind of helpful to kind of see that, make sure that the model's configured and behaving the way you think it should behave. Eventually one will come up, I think. There. I'll just pause it. So in this case, there's no open boundaries. If you had open boundaries, they'd be summarized down here, and it would tell you total flow across your open boundaries through each of your 4 different east, west, north, and south, and then the total inflow and outflow. And this was configured for real-world cases, so the flumes, the rounding of the precision of the output is showing 0 because it's so little flow from a cubic meter per second perspective. But anyways, this has the big. You might want to delete this if you want to run multiple runs on the same computer, because it's quite possible if I've got 4 cores and I want to run one model with 2 cores and another model with 2 cores, I can do that with no problem. However, I have to tell EE and EFDC and the batch file generator how to do the offset, and that's what this is here. So if I tell it, okay, I want to run model with 2 cores, and I want to run another model with 2 cores, the second model would simply put a 2 there, and it'll just offset them. Yep. So this model will run with these 2 cores, and the second model will run with these 2 cores. And they, other than I/O, they basically won't interfere with one another at all. And if it gets a little confusing, 2 things. Number one, there is a little guide tutorial thing on our website you can download to kind of give you more detail on what's going on here. If it's just not working for you, and it's causing you problems, just delete that KMP affinity line directly from the batch file, and then just run the batch file. And then what it'll do is you'll still get the same number of threads that you're asking for. Actually, let's show you that. I forgot to show you that in the batch file here. The actual number of execution threads is specified right here. That's all you have to do to change the number of threads applied to your run. So here you have your executable, the path to the executable name, and then there's only 2 command line options on the EFDC plus. There's NT for the number of threads, and it can be 1 to whatever. And then the second one is NOP for no pause. If you have calibration statistics configured in the model, you can click this button here, and when the model finishes, EE will automatically go out and process all your calibration statistics for you, which is kind of nice when you've got, the model finishes in the middle of the night. And it takes a few hours to process all, read the files and go through all the processing, and when you get in the morning, it could all be done. All your plots are sitting there in your output folder, or your analysis folders. So anyways, now let's look at this this is the case where we don't have morphology turned on. So now let's look at this and notice that it kind of defaults to that. Well, I've already configured all this. I don't want to have to do it again. So I'll just load it up. So I don't have to reconfigure everything. And this is a little bit of a bug. It just doesn't display the first time step for some strange reason. Then after the first time step, it shows up. So it's a little bug in the displayer processor. But let's turn on the animation now. And what you'll notice now is the bed elevation is not changing. See what's happening to your sediment column. It's still eroding, but now your sediment column is being impacted by erosion and deposition. And interestingly, when you turn off morphology, you get really quite a different behavior in the model. Move this out of the way here. We can look at it by comparing models. And we'll do that here in a second. But now, so we're past the peak. We're on the recession limb. Bed elevations are not changing. But look how much erosion has occurred in that reach there. And then at the end, let's see, it takes two hands to use this keyboard. The very end of the run, I get a fair amount of erosion in this area here, and I don't think I saw that in the morphologic model, the morphologic feedback turned on. And then this is kind of interestingly, it just kind of removed all the sediment in almost a little uniform manner right down there at the bottom. So let's play around with this and do a model comparison. Well, let's look in the plan view first, just what it looks like plan view wise. So go to sediment bed, look at thickness, and because everything is accumulating in my model in this cell down here, you kind of have to play, the automatic scaling doesn't work as well in this case because I just have a bunch of water and a bunch of sediment accumulating in my accumulator cell. So it's a little bit better if you don't allow auto ramp and you fix these parameters. So let's say 0.15 and 0.25, something like that. And that will then fix your parameters for the animation. Move this out of the way. Yeah, put it right here. Get that out of the way. Screen doesn't have a whole lot of real estate to work with. Slide that up. And once you kind of get things like this, by the way, again, we have a way to save this so you can come right back to it. So I'm going to do it since this is a special case for me. Do Alt-K, and I'm going to save it out. And instead of a DSG, these are V2D for the view for 2D, and then we have a view 3D for the 3D display. So I'm going to pop this up one level and save bed thickness V2D so I can generally get this layout without my legend laying on top of it. And that, the V2D actually does set the size for you, so you don't have to, you just load that one thing and everything gets set. Now, let's animate and see how this looks by comparison, what we remember from the prior model. So without morphology, looks like we're getting more erosion here, actually getting more erosion there, but not, don't see quite the buildup that we saw, or the scour hole coming out here, and that buildup here is no longer at the quote-unquote point bar location. So how about we compare the models straight up? So we go to model analysis and load up a comparison model, and we can load two models and then do a delta between them and be able to see how one model compares to the other for the same parameter. So in this case, we'll be able to see the difference between the revised model and the new model and its bed thickness in a map, and we can animate it and do anything you want to do with it like that. So we're going to load up the comparison model. And this tool does not require a one-to-one correspondence for cells. And the reason for, obvious reason for that is one of the very standard applications of the model is you have a base case and then you have an engineering case where you have done something to the model. And maybe you have, you put in a pier or a new, embayment or something that changes the actual grid. All there has to be is they have to overlap one another somewhere. And if it does, it matches, it pairs the model to model and finds out what cell in this model matches to what cell in this model, and then it'll just do all the comparisons based off of that. It takes a little bit of time if you've got a really big model, though, but it does work nicely. So I'm going to browse to my base case, which was with morphology. And it reports back, information about the model. Now this field here, you have it on the input file, and you also have it here. The only reason why ever to use that if you're loading a legacy model from, typically like from Tetra Tech or somebody that's been using the EPA version of the model, because a lot of times they use, their coordinates are in kilometers in the LXLY file and not in meters. EE just keeps everything in meters, so your coordinate that's in the LXLY file will be in meters, and it assumes so. But if it's kilometers, all you got to do is change that to 1,000, and it'll scale the coordinates in the LXLY file to meters. Or if it's in feet, you can convert it to meters. But anyways, EE wants it in meters. Now, give it a name. This is no morph, and this is morph. Whatever name you want. Now, another important factor here is time tolerance. Because sometimes you may be running a model, and one model may be output at 1 hour snapshot, another model may be output on a 3 hour snapshot. And so we apply some tolerance value that says, okay, models have to be at least within this delta to consider them the same snapshot. So in this case, we're using 1 minute output, so really this should be something more like anything under a minute, 0.1, 0.5 will work fine. I think it was beginning in 7.3. We started writing all timeout in double precision, and doing everything in the inside the model is hardwired double precision and hardwired in EE double precision, because you've got days, Julian days in thousands or tens of thousands, but you're dealing with very small delta T's. You lose your resolution because it all gets lost in the machine precision. So anyway, just a small little usability point. Hit enable model comparison. Went out, read the comparison model, read 180 snapshots. Go to the plan view. I'm going to load up that view that I looked at so I don't have to move everything around. Alt-L. There it is. Now this is another, this view, I had bed thickness displayed. I may not want that. So if I said open, it'll ask me if I say yes, it'll open, it'll change all my views to whatever's in that file. All the settings, views, color ramps, everything. If I say no, the only thing it changes is scales, position of the plot, etc. So I'm just gonna hit no, and you can see it's kind of rearranged everything for me. But now I'm going to go to thickness, and now I want to do a comparison. Hit F2. Here you can see Alt-M should be here somewhere. Where is Alt-M? Alt-F, you are just below where I can see, huh?
One line.
Oh, there we go. Scroll up. Yep. So, basically, it's just a toggle. You can toggle on and off your model comparison. Once you have a comparison model loaded, it stays loaded and is available for compare until you either load another model or you do something to affect that model. Once you make a change to the model, you lose the model comparison. You can always start it back up again, but it's in memory and available, and it'll do your base model minus the compare model. So, when I'm there, there's another little kind of user trick. Sometimes the Alt and function keys don't work when you first press them. It all has to do with what's called focus. If something doesn't work, and it says, oh well, Alt-M should work, and you hit Alt-M and nothing happens at all. It's because something else has focus on the model right now. It's little mini thing we need to fix, kind of make it a little bit less secret. But anyways, if you just click anywhere over here on the actual form, and now hit Alt-M, it goes out and does a thickness compare. A delta, and should all be 0. Why is it 99? Oh, that's right. That's what it is. Is that for whatever reason that first snapshot's not being saved? There we go. So now what you're looking at actually is the difference between the no morph condition versus minus the morphology condition. So here, in all cases, at this point right now, the morphology case is all higher than the morph case. So this one actually has more scour at this particular case. And as we scroll through it, you can see how the behavior of the models are different. I'm not sure that thickness is working quite the way I think it should. I'm wondering if it's actually doing a delta. Because this number here should be more like 0. Let me go to this. Bottom elevation. It does not. Oh, that's right. Whenever you switch views, it always does that. It always turns off model comparison. Yeah, so here we go. I'm not sure the bed thickness works quite the way it's supposed to be working. So I know this one works. It's something I need to check into. It looks like it's not doing it. But this is behaving more as expected. Sorry about that. Here we have an area where you, so the negative, of course, is the bed elevation or bottom thickness of the bed is higher than with no more. So when it goes negative, so and showing that there's more scour with the morph condition than there is with the no morph. And you see the patterns and the difference between having morphology turned on and having it turned off. And it just keeps getting bigger and bigger as the simulation runs. So turning on morphology is, obviously in this case, it's designed to have a big impact. It will have less of an impact than many cases that you guys are typically dealing with. But honestly, it doesn't really add much computational burden to the hydrodynamics. There's not a whole lot of reason not to just by default turn it on for the most part. If you think at all there might be some impact to your hydrodynamics from your sediment transport. All right. Anything else, you guys? Another thing that can have, well, it does, and it certainly will have an impact on your sediment results, is your sediment time step. And this is something that's kind of, now that you've got the model set up, it's easy. You usually start with a small, almost a one-to-one correlation, if not a one-to-one correlation between your sediment time step and your hydrodynamic time step. And just start increasing your sediment time step and kind of see how the model deviates from your one-to-one correlation or your one-to-one model run. And that is a nice way to kind of pick, oh, well, I can be up to 20 times before I see any kind of significant difference. But there will be a difference. The same thing applies to water quality and toxics and all of them. The question is it significant? I mean, given all the other tuning parameters, if you can get the model to run faster, and that's always the goal, get the model to run faster and end up with a good calibrated model, why not do it? You don't have to keep the one-to-one correlation. I mean, as we were talking about this morning, coupled models, they use of course, the difference is this is an instantaneous value that it's computing at every 1 second, which is 20 snapshots. So it's calculating your sediment deposition erosion processes in a 1 second interval at that particular instant in time when it does the calculation. The coupled models are using a residual flow field or an average field that takes that period of time, and so you get the range of information that was in that integrated into a single number. So you can have these much longer, like 5-minute, 10-minute, 15-minute kind of coupling snapshots. If you were using a coupled model, you probably don't want to use something quite so large with this version of the model, in the coupled model. Not the least of which you want that hydrodynamic feedback. So that happens on a smaller time scale. Other things to you guys saw, play with that. So this just kind of shows you, as I said, this just kind of does some calculations for the different parameters for your size classes that you have defined. And yeah, just gives you what it did. And if I hit this value button here, it'll set them to whatever those calculated values were. And I change something, I say, oh, I didn't really mean to. You can cancel, just like anything. Go back to it and be good. What happens is it uses a fractional step solution. So, okay, first we solve the solution for the pressure field. So we get essentially, what the water surface elevation looks like everywhere at the beginning of the time step. Then we calculate the velocity field. And then from that velocity field, then we calculate the amount of material that was eroding and depositing at the sediment bed. So at the end of that time step, the sediment bed will have dropped if it were eroding. So now it's but the depth in that cell that dropped also dropped just a little bit in the pressure solution. So it marches that forward to the next time step. So now you have a lower bottom elevation, the same water that you had essentially, assuming that things are not changing that rapidly anyway. So the depths are the same. Then it resolves the pressure solution, and that as it drops down, water will move in to fill that void. So you have a nice smooth pressure solution. If I wanted to animate water level, every single time step, you'll notice that your maximum depth, because it's all flowing off into this tank, that's 1 meter square, and it's just filling up, and it ends up with like 600 or 700 meters of water in my theoretical catch basin. Exactly. So what you have to do is you just have to manually fix it. So this is, I want to go from 0.1 to say 0.5 or excuse me, I think it's like 0.25. Whenever you type, you'll notice that here, let me just cancel this. So when I go in here, you'll notice that the auto ramp is checked. So if I want to turn off auto ramp, all I'd have to do is that. Conversely, all I have to do is type anything into this field, 0.4, and notice the auto ramp automatically just unchecks. Because it's assuming that if you're changing it, you don't want auto ramp to be on, because it'll overwrite whatever you just put in there. You also have the ability, though, and this is kind of nice. So now when I turn this animation on, it's actually, let me drop this way too big. Let's make this 0.14 and 0.1, something like that. And yeah, now you can see a little bit more of a gradient. Oh, what I was getting ready to do is so this, when I turn on the animation, now it won't change. And that's, a very important factor because if you're ever watching an animation, the scale, max and min value keep changing. It's really hard to interpret. You have to fix those scales for the animation, or otherwise it's just too much for the mind to kind of take in that, oh, that scale is going up and down all over the place. So anyways, all that to say that fix the scale. Now, there is a nice feature, and I use this a lot, is this auto scale with view. And if you click on that, no matter if this is on auto ramp or not, but you notice that this is being picked up. It's 583 meters deep. But if I just zoom in just to this area, then it'll only do the automatic scaling, but only on the area that's currently being displayed, which is really helpful, when you're looking at big models, especially like at a river model, and you've got all elevations, going, you're dropping 40, 50 meters, or more, your scales, you can't see anything, but you zoom in, this is really a helpful feature. There is a tool in the model analysis tool that is very helpful. It's under the miscellaneous tab, where we just have thrown together various and sundry tools. If you're running dynamic time step and you want to know how did the model perform, you just click on that button right there, and it'll just generate a plot and show you what the delta t was throughout the model simulation. Kind of nice. You can do some vertical slicing of the grid, which is kind of helpful. These down here are real nice for looking at details of what's going on in a single sediment column. You can watch the sediments grow and shrink, reports back void ratios and various and sundry statistics or model results from a single sediment column. It's not very robust, in the sense of user, you have to actually type the I and the J, but it works. But what I want to talk about here is the mass balance tool. So if I click on the mass balance tool, you get this form here. Now, this particular model, this flume model, was designed so we have really good control over the mass balance. So if you are simulating a system that has an open boundary, the flows in and out of that boundary are calculated by EFDC at every hydrodynamic time step. EE will calculate a flow at an open boundary. However, it's only at the snapshot frequency that you're outputting your snapshots at. So if I'm outputting every 15 minutes or an hour for some hydrodynamic model, when I calculate a mass balance, I'm essentially linear interpolating between my snapshots with my mass balance. So I call it's an approximation of a mass balance. What's helpful about it is it kind of puts things in kind of general categories so you understand, oh, well, this flow boundary, contributes 85% of the total flow coming into the system, that kind of thing, helpful. But for a really highly precise mass balance, either the system needs to be totally controlled by flow boundary conditions, so that you have a control over exactly what your flow rate is in between your snapshots, or you do something like this, which is can't do in real world, but you totally capture 100% of your flow in this hypothetical tank I built. So you have by default all the parameters that you're simulating. Now, you can do a mass balance around the volume. You can do a mass balance around total sediments, but in this case, cohesives and total sediments produce the same number. So you can specify a period of time that you want to do the mass balance around. And you can generate time series of your mass balance numbers for the simulation. So let's just say I want to come down here to total sediments. And I'm going to view the time series, and I just click calculate mass balance. Goes out, reads all the data file, and then generates mass balance error. And not sure even why that's as high as that is, although it's a pretty small number. But we started off with 12 metric tons of sediment in the sediment bed. At the end of the run, we had 11 metric tons, rounded off to the nearest, whole metric ton here. The sediment lost 0.657 metric tons. The water column gained 0.65 metric tons in that period of time. Yeah, this has got the morphology turned off right now in this particular run that I'm looking at here. And then it also then calculates your total fluxes through your flow boundaries, your any hydraulic structures, all your open boundaries, how much water is coming in from rainfall and evaporation. Groundwater is missing here, actually. So that's a little tweak we'd probably have to make. And then calculates a total mass of sediment lost or gained, and then calculates a percentage. It's calculated a percentage based on the initial condition mass. So anyways. Oh, well, let's see here. Actually, I know what the problem is. This is what I was explaining. Yeah, well, here, let me just show you the curve, and then I'll explain what the issue is. This, we've got, total amount of mass in the sediments, in the water column, etc. Right now, oh, I'm assuming you guys know if you can click on this button here or right mouse click on the legend and it brings up your all your series. You can turn off and turn on whether you want to see them or not. So it's a really small number, but you see this kind of behavior for your error term. Now, what I was going to show is that I'm using a single precision model. You want to improve that, you need to use double precision. You don't need to use double precision for many applications, but there's a lot of applications that are out there actually where I have found that I needed double precision accuracy to get the answers that I want, because if your system is large and the processes are slow, you get round off. A classic example, heat exchange at the bottom. So you have a water body and you want to account for the amount of heat exchange across between the bottom layer of the model in the water and the sediment bed. That rate of heat exchange between the water column and sediment bed, really small rate of change. The heat flux is quite small. So if I have a temperature of 20 degrees, I have a delta T of 2 seconds, and I'm applying a heat exchange that's 10 to the minus 6, I have just lost that heat exchange completely. It's 0 because it's below the smallest value that a single precision number can account for. Now, because that's such a common problem, we changed the heat exchange code in the EFTC, lots of changes, but one of them is we accumulate heat exchange until it reaches a certain critical level and then roll it into the actual heat exchange between the sediment bed and water column. So we just accumulate it, and that helps us get around that issue. But those kinds of processes, kinetics, anything that has a rate of change that is really small relative to the domain that it's going in and out of, you can lose that information in round off. And that's what happened here. This is the single precision model. I run this double precision, and that mass balance drops to essentially 0. So now I'll stop.